Imagine a perfect mathematical model of space, tearing at the edges, because the glass looking at it is flawed. This is exactly what happens when you take standard photogrammetric mathematics, equations built for large, high-end lenses, and apply them to the miniaturized, mass-produced CMOS sensors found in everyday mobile phones. This residual vector field from a tested mobile sensor shows the mathematical signature of that exact failure. The arrows represent a sweeping, directional flow of uncorrected errors traveling across the image plane. The mapping industry is currently shifting from heavy, expensive terrestrial systems to mobile 3D modeling. That transition relies entirely on ubiquitous, lightweight edge devices capturing accurate spatial data. But miniaturized optics are manufactured under severe cost and size constraints. This introduces bizarre, highly localized physical deviations into the images that traditional error models simply cannot process. By deconstructing these specific residual patterns, we can map the exact limits of standard self-calibration. More importantly, we can prove how sub-millimeter spatial accuracy is mathematically recoverable, even from deeply flawed hardware. To isolate a camera sensor's internal optical errors from general environmental noise, researchers require absolute laboratory-grade experimental control. For this test, they utilized a tightly controlled 3D calibration field containing 87 targeted points. The scale of this object space was defined by interferometry to an exact length of 1,000 millimeters. This diagram shows the robust convergent imaging network utilized to capture that test field. You can see the spatial arrangement of the 13 numbered station points surrounding the target volume. To extract the target coordinates directly from the raw image data, the team used least squares template matching. This computational approach ensures the measurements are free from human manual measurement biases. Because the baseline theoretical precision of the test field's control points is nearly perfect, down to plus or minus 0.03 millimeters, any spatial deviations detected during processing are strictly the fault of the camera's internal geometry. The first major physical defect found in cheap mobile sensors occurs during assembly. The microscopic mounting between the CMOS chip and the molded lens is often highly imprecise. In the tested Nokia N93 camera, this imprecise mounting resulted in a massive shift of the principal point. The offset was measured at an extreme negative 109.8 microns along the x-axis, far from the theoretical true center expected in a standard still video camera. Traditionally, photogrammetrists fix these types of optical errors by applying standard radial and decentering lens distortion models. These plots show the exact radial and decentering distortion profiles calculated for the test cameras. The top graphs display the smooth radial curves, while the bottom plots map the sweeping decentering grids across the image plane. But the data revealed a paradox. The camera exhibiting the smallest magnitude of both radial and decentering distortion, the Sony Ericsson K750i, yielded the worst absolute geometric accuracy in the physical object space. In miniaturized optics, measuring the sheer magnitude of standard distortion is no longer a sufficient predictor of the sensor's final metric quality. The physical flaws are far more complex. To mathematically flatten these complex error fields, engineers apply a self-calibrating bundle adjustment. This relies on block-invariant polynomials, specifically Brown's 10 or Grün's 44 additional parameter sets. These standard mathematical sets were designed decades ago. They were built to correct the mechanical instabilities inherent to traditional SLR cameras, like film flattening issues or subtle lens body shifts. This plot of image 13 shows what happens when those robust parameter sets are applied to mobile CMOS data. Even after the corrections are run, a persistent, systematic wave pattern of uncorrected directional vectors remains highly visible in the bottom plot. The physics behind this failure come down to scale. Cheaply molded microlenses introduce highly localized, complex warps into the light path. These microscopic anomalies cannot be mapped by polynomials built for large, uniform glass elements. The standard mathematical toolbox is broken for this hardware. To truly flatten the field, miniaturized optics require entirely new, customized error functions. There is one final variable that professionals historically assume destroys metric accuracy: lossy algorithmic image compression, specifically the JPEG format. Look closely at this zoomed-in target dot. You can clearly see the visually destructive degradation, the heavy pixelation, edge ringing, and block artifacts caused by the mobile camera's forced JPEG compression algorithm. In a theoretical ideal system, uncompressed image files preserve perfectly sharp edges, allowing measurement algorithms to locate targets with absolute certainty. Researchers compared an uncompressed TIFF baseline against files crushed 42 times to a quality 70 JPEG. This chart tracks the resulting depth accuracy. The result defies intuition. This massive visual compression degraded the depth accuracy by only 12 microns. The data proves that visually destructive high-frequency noise does not inherently break the sub-pixel geometric spatial fidelity required for close-range template matching. These mobile sensors faced massive principal point shifts, completely unmodeled systematic distortion fields, and severe JPEG compression noise. This 3D plot shows the final absolute accuracy numbers for the tested CMOS device, proving the raw geometry survives. In the object space, the root mean square error hit 0.036 millimeters on the x-axis, 0.101 millimeters on the y-axis, and 0.030 millimeters on the z-axis. Furthermore, multi-month temporal stability tests confirmed that these bizarre distortion signatures are not random environmental noise. They remain permanently stable and mathematically predictable over time. Despite severe physical manufacturing constraints, miniaturized edge sensors are legitimately metric capable. They achieve consistent sub-millimeter accuracy. To fully unleash ubiquitous mobile hardware for true 3D modeling, the photogrammetry industry must stop relying on DSLR-era math. The path forward requires engineering novel correction polynomials that map the